In the last section, we took a look at a special kind of discrete distribution that was known as the binomial distribution. And there are many other types of special discrete distributions, in fact, even more than what exists on our formula sheet. Remember, the front side of our formula sheet covers a generic discrete distribution, the binomial, and two more discrete distributions that we'll talk about in this section, the geometric and the Poisson. Now, there are many other discrete distributions besides the ones listed here, but these are going to be the focus really for our course. We're going to start by taking a look at the geometric distribution and see kind of generally how this distribution behaves and how is it similar and different to the binomial. Well, let's take a look here at example number 1. A major oil company has decided to drill independent test wells in the Alaskan wilderness. The probability of any well producing oil is 30%. Now, this problem may seem familiar. We actually dealt with this problem back in our section on independence. But we're going to see here how this is going to relate to the idea of a geometric distribution. So let's take a look at part A here. We want to find the probability that the second well that is drilled is the first one that produces oil. So if I was to go ahead and actually think about what it is that I want to have happen, I can think again about having a successful event, which would be something like find oil, and I can still have the idea of a failure, which would be not finding oil when I actually go ahead and drill a well. Now, I'm going to go ahead and just abbreviate these as S and F to make them a bit simpler to work with. But what I can see here in part A is that what I want to find is a failure to happen on the first drill, and then in S, or a success to happen on the second drill. Now, if these are, again, independently drilled, then that means that I can calculate this by doing the probability of F times the probability of S. However, I should know both of these values because the probability of successfully hitting oil is 30%, which means that the probability of failing to hit oil would be 70%. So, when I take these two values and multiply them together, I get 0.21. So there's a 21% chance of having the second well be the first one that hits oil. We'll take a look at how I'm going to generalize this. What about if I wanted the third well to be the first to produce oil? That would mean that I would need a failure, and then a failure, and then a success. Well, it's still independently drilled wells, so I can go ahead and rewrite that as the probability of F times the probability of F times the probability of S. Notice that's going to ultimately just get me a 0.7 times another 0.7 times a 0.3. If I multiply this out, I'm going to get a much smaller percentage of about 14.7%. Okay, well, let's take a look at part C. What's the probability that the fourth well is the first one that produces oil? Well, that means I'm going to need to have 3 failures in a row, so the fourth drill is the first time I hit a success. So that would be the same as probability of F times the probability of F times the probability of F, and then multiplied by the probability of S. That would be 0.70 times another 0.70 times another 0.70, and finally times our value of 0.30, which comes out as a grand total, if I crunch this all out in my calculator, of about 1029. So I can kind of see here how all these questions are sounding the same. The only thing that's really differing each time is which well I want to be the first success. Notice down here on part D, I can fully attempt to kind of generalize what I'm working with here. What if I wanted to find the probability that the nth well, like a mystery number well, is the first one to produce oil? So like, I couldn't really be sure at the moment of how many failures I want. I know I would want kind of a couple. I'll illustrate that by saying that I'm going to have a ... in here. And then I'll hit a failure again, so I have a big string of failures at the front, and then finally a success. Well, that would really mean that I'm going to have a bunch of 0.70s multiplied in a row. I'm not really sure how many, but a whole bunch of them. And then I would end with my 0.30. So if someone was able to tell me ultimately what well they want to be the first one to produce oil, I could easily tell you how many 0.70s would be in the calculation. Because I would know that if 0.30 is over here at the end, and if this is, say, well number 10, then there should be 9 wells before it. If this is supposed to be well number 50, there should be 49 wells before it. If this is well number n, then there should be n minus 1 wells before it. And so that means that I could actually express this with kind of an exponent, where I'm going to have number of wells minus 1 will be failures, and the last well will be a success. So this is how I could generalize this, and now I would actually have a formula here. This generalized pattern is what we refer to as a geometric distribution. If you take a look at what's in the box here, you'll see that I say that this is a discrete distribution where the random variable x represents the number of independent trials that is needed to obtain one success, or a first success. And so I can see it even has this kind of same basic general formula here. In place of p, I have my chance of success, which is hitting oil. Then I have 1 minus p for all of my failures. And I have a power with a minus 1 on it to indicate that I need to have 1 less failure than the total number of attempts. So one important key thing here is to note that these need to be independent trials. And if I don't have independent trials, I can't have something geometric. Now fortunately, we won't have to do big calculations like what we did up here because we have some nice calculator commands. We'll have a geometric PDF, very similar in behavior to a binomial PDF, and a geometric CDF. Of course, though, here there is no n value to enter, as you can see. We only need to enter a value of p, our chance of success, and the value of x that we're interested in finding the probability for or stopping at. And in the next video, we'll take a look at an example where we can kind of see how this plays out and see how we can use the formula sheet to help guide our thinking.